Newton's method is something that in general you do not want to use in machine learning. And the reason you do not want to use it in machine learning is because it requires you to know information about the second derivative of the function that you're trying to minimize. And understand that in the context of machine learning, that is potentially very costly and very hard to get. But the benefit of Newton's method is that it's potentially way, way, way faster than gradient descent, because you can use that second derivative to decide what is your step size. One of the key problems that I wanted to highlight with gradient descent is that that parameter eta, that step size, it's a free parameter that you have to choose. If you're lucky, you might be able to prove, that there's a range of eta that will guarantee convergence, but in general, that's not the case, and you have to play with the value of eta. But Newton's method is an example of a situation where if you have more information about the function, you can adapt the value of eta pretty much automatically without having to really do much. So the idea of the Newton method is to, again, perform an update to go against the gradient of your function at any given point to find the next possible candidate to minimize the function. But this time, if you look at the expression that I'm writing you for the update for the Newton or Newton-Raphson method as it's called, you'll see that there is no free parameter anymore. There is no eta that you have to choose. Instead, what I involve is a quantity, which is the inverse of the Hessian of f at x. So I'll redefine in a second what is the Hessian, but understand this is if you want an adaptive step size. All right, so the idea is that you're going to automatically tune your step size to the local geometry of the function, here in the form of the inverse of the Hessian. The reason I'm mentioning that is that if you ever play with such algorithms to optimize neural networks, you never do Newton-Raphson because that's too complicated and too costly to evaluate or estimate a Hessian. However, people have still tried to come up with many techniques that avoid having you tune a step size, but rather simply have you come up with a rule that forces you to adapt the step size to the geometry of the function that you're trying to optimize. So the inspiration is definitely coming from Newton-Raphson, even though they don't use Newton-Raphson as such. So the Hessian matrix, just to remind you, is the matrix that contains the second order derivative of the function x with respect to all the pairs of coordinates. So if your vector x has d coordinates, x1 to xd, the function, the Hessian simply contains the derivative of f for the 2, so it's a matrix that contains d to f over dxi dxj for all ij between 1 and d. Okay, so you're just aggregating all these second order derivatives together. Now, the formula I gave you in star here, that expression for the Newton-Raphson method, it might look a little bit like magic, but there is actually a very nice interpretation of where this comes from, and we can actually justify why, if you know the Hessian, this equation star is actually the right thing to do. And I'm going to illustrate that slightly informally, but that's the justification of the approach. Justification. Okay, so our goal here is to come up with a heuristic explanation for why the Newton-Raphson method has the form that it has in the previous slide. So the first thing that we're going to do is we're going to say, okay, I have a function f, so let me try to illustrate things here. So f of x as a function of x. And so my function f could be something like this. I'm drawing it convex just to make my life easier. And what I'm going to do is I'm going to form a quadratic approximation of f at a specific point that I'm going to call x prime. So let's see, this is my point x prime. And my goal is to come up with a quadratic approximation of x prime. Quadratic approximation means I'm going to try to find a function which is quadratic, but locally follows the function f. And that function I'm going to call f tilde. Okay, so we consider f tilde a quadratic approximation of x prime of f of x, sorry, a quadratic approximation of f at the point x prime. And so what it means is it means that I'm going to write f tilde of x as follows. It's going to be f of x prime plus, I'm going to add the first order term in my Taylor series, so it's going to be the gradient of f of x at x prime. I should be a bit careful. Let me make sure I use the right terminology. So I want to find an approximation at x prime. Let me call that x star rather than x prime. So I'm going to call that x star. So f tilde as a function of x is going to be f of x star plus the gradient at x star times x minus x star. That's the first term in my Taylor series. And if I want to do a quadratic approximation, I need to add the second term in my Taylor series, which involves the Hessian. So I get x minus x star times the Hessian at x star. I'll put a transpose here, x minus x star. So this is essentially the Taylor series truncated after two terms. That's what my approximation is. Now, let's say now that you think that your approximation of f by f tilde here is pretty good. What's very natural to say is to say the following. Well, given that I've done that approximation, how will I find the minimizer of f? Well, let me try to find the minimizer of f tilde. If f tilde is a good approximation of f, then the minimizer of f tilde should be a good approximation of the minimizer of f. So let's try to do that. So how do we find the minimizer of f tilde, which is a quadratic form? Let's find the gradient. So the gradient of f tilde evaluated at x is what? Well, if you write, you take the derivative of the form that I wrote here, the first term f of x star is just a constant, doesn't show up. If you take the derivative of the second term, anything that only contains x star is a constant, that goes away. So the first term that will show up is actually the gradient of f of x star. It makes me realize that I might have forgotten the transpose here. And then we need to add the derivative of that quadratic term here. And again, we've seen calculations like that when we derive the maximum likelihood estimator in an example. And we had to do a little bit of differential calculus here. And by the same token, we can prove here that the term that will matter will be a term that is now linear in x, if you wish. And the only thing that will matter are, let me see, I want to make sure I'm not forgetting signs. Okay, so I have two terms to worry about. One that contains x twice, and that term here will have a factor of 2 that will show up because it's a squared term. So we'll get a term which is simply going to be the gradient square of f that I evaluate at x star times x. And then I have a term that will correspond to the cross terms that will depend on x star. And so the last term that I will have is minus the gradient square of f of x star times x star. Okay, so I'm taking the derivative or the gradient of f tilde of x. And now I'm going to say, well, given this, let me try to find the minimum of the function. Okay, so we're going to update our sequence of points to find the next minimizer by saying my best guess is to take the point that will minimize f tilde viewed as an approximation of f. So if you do that, so assume that we update in gradient descent from the point xj to xj plus 1 by minimizing f tilde. Right, so the reason you can do that is because f tilde is a quadratic form. It has potentially a much nicer expression than f. So let's write what that means. So it means that you want to find the point where the gradient of f tilde is 0. So if you write the gradient of f tilde of xj plus 1 is equal to 0, what does that mean? Well, it's equivalent to saying, according to the expression that I had before, that the gradient of f at the previous point, which is xj, plus the Hessian of f at xj times the point where you're evaluating, xj plus 1, minus the gradient, not the gradient, the Hessian of f at xj times xj. This has to be equal to 0. But equivalently, if you rearrange things a little bit and you try to express xj plus 1 as a function of everything else, what you will realize is that it means that xj plus 1 has to be equal to what? It has to be equal to the inverse of the Hessian at xj minus 1. That's how I get rid of the constant in front of xj plus 1, times an expression which is the following. The Hessian at xj times xj minus the gradient of f at xj. And noticing that here I have the inverse of the Hessian, here I have the Hessian, you obtain exactly the following expression. Xj plus 1 is equal to xj minus the inverse of the Hessian times the gradient. And so you see that the justification for Newton method is that you're doing this local quadratic approximation of the function, and you're using that as a surrogate function to decide what is the next optimal point to choose. The reason there is no step size, if you wish, is because implicitly you are choosing the step size based on the Hessian that captures how to approximate the function quadratically. And as you can imagine, what's happening is that as your function gets flatter and flatter, as you're trying to start, you zoom in hard enough, you start reaching your minimum, then your step size will adapt to that. But on the contrary, if your function is very steep, potentially the quadratic fitting will also be very steep and you'll move more. So you have an implicit adaptive step size that goes on, and that's really the reason why it works. Now again, the reason you don't want to use that in many applications is that it's very slow, but when it works, it is way, way faster than all the gradient descent technique. Maybe the one thing I wanted to reiterate here is that if you look at the Hessian here, it is a matrix, and the dimension of that matrix is d by d, by definition. And so you have d square entries to compute. As d gets large, computing that matrix becomes really tricky, and that's why you tend not to use it. And inverting it in particular, that's very costly. The inversion of a matrix that scales as, the size, if your n by n matrix is n3. So that grows really fast with a dimension that's undoable if you have a high dimensional feature vector.